Hi again. So now we're going to talk about the last step or the last stage in this process, which is the waveform generation. So already the DNN has already produced or has already predicted feature streams, Melchepstra band aperiodicities, interpolated F0 and voice indecision with their respective deltas and delta deltas, and then we need to go back to the vocoder, raw vocoder features, so the vocoder then can produce the waveform from these parameters. Okay, so the first step here is to feature engineering, but reverse feature engineering, as we explained in the feature extraction. So the first step is just we denormalize. We just recover the normal ranges or the original ranges of the data. Okay. Then, as we mentioned, thanks to our question, is that the DNN produce frame by frame data, frame by frame features, and unfortunately, they are not the trajectories of these features is not smooth. Okay, they jump, even though we use our recurrent neural network. Okay, so we need to use this system, this method called MLPG, which is like a statistical filter, which is smooth in a correct way, in a good way, the features. Okay, then after that, we need to just recover the spectral envelope from the compressed Melchepstra. Just we take these smoothed features, smoothed Melchepstra, and we convert back to frequency domain, and now we have the spectral envelope with the length of the half of the FFT length. Okay, we do the same for the F0. We just do the inverse processes that we already explained in the feature engineering. Okay, so at the end we have these three raw vocoder feature streams to feed into the synthesis part of the vocoder. Okay, so we take the synthesis module of the world vocoder, and the first thing that it does, it creates a train of pulses, okay, in time domain, in waveform domain. So it generates this train of pulses, and these pulses are 5 milliseconds apart if the segment is unvoiced, and if the segment is voiced, the distance between these pulses is the fundamental period, which is 1 over the fundamental frequency. Okay, in that way we will generate the pitch, the required pitch, which is the frequency how our vocal folds vibrate, right? So after generating this pulse of train pulse, we start working with the spectral envelope, the first of the one of the features that we extract, right? We have. So the features are generated by the DNN frame by frame every 5 milliseconds. But now we want to get the features, the correct features in the pulse locations. And the pulse locations sometimes can match the locations of the frames, but sometimes, most of the time, they don't. So we need to interpolate the data. We need to interpolate, in this case, the spectral envelope that we have in frame n, in this case, and frame n plus 1, and just linear interpolation in that way we have the spectral envelope at the pulse location. So once we have the spectral envelope at the pulse location, we need to reconstruct the periodic and the aperiodic spectral envelope. Okay, so that's the blue line, is just the spectral envelope, and also we have the aperiodicity. Okay, these two curves, these two features are in the input of the vocoder, at the input of the synthesized module of the vocoder. Okay, and if we do some mathematics, or the world does this in the code, at the end it will produce the periodic spectrum, which is the green line, and the red line, which is the aperiodic spectrum. Okay, so at the output of this process, it generates the green line periodic spectrum, which has more energy in low frequencies, and in high frequencies it has less energy than the aperiodic spectrum. And another way, the periodic spectrum has less energy in low frequencies and more energy in high frequencies. Okay, so this is the standard case of what happened with voiced frames. So when the frame is voiced, the periodic spectrum has more energy in low and less energy in high frequencies. Okay, so we have these two vectors, the periodic spectrum and the periodic spectrum, and then world, as they are just defined in magnitude, we need like to append or to create a phase to append to this magnitude to complete the complex spectrum that could define a signal. Okay, the signal is not just made by the magnitude. We just need to create a phase response. As the phase was not modeled by the DNN, the world just create from scratch or invent a phase. Okay, and that phase is the type minimum phase. Okay, I'm not going to go into deep what is minimum phase, but it's just one type of phase that is appended to this magnitude. And then once we have this magnitude and phase, we can create the complex spectrum. Okay, and that is done for the aperiodic spectrum and for the periodic spectrum. But the difference is that in the case of aperiodic spectrum, as this is just the envelope, we need to add some randomness, some aperiodic energy. So to add that, we just multiply the aperiodic spectrum with the spectrum of random noise, with just artificially generated random noise. And then after that, we go back to time domain by just IFFT in the aperiodic spectrum and the periodic spectrum, and then we just add the two input responses in time domain. We add these two. Okay. Then once we have this addition of these two input responses, the aperiodic and the periodic, for each frame, we just need to overlap and add. Okay, following the pulse train that was constructed at the beginning of the process. And at the output, we'll have the synthesized waveform. So, we can now we have more information, and we can just rethink about this question. So, what's better, fixed frame rate or pitch synchronous? We see again that the world internally, or this vocoder internally, is working in a pitch synchronous fashion. So it needs to interpolate these features generated in a fixed frame rate. So maybe it's not the best solution to use fixed frame rate. Another thing to think about is that maybe the feature extraction and in the synthesis, they shouldn't be necessarily be like symmetric, or just one is the inverse process of the other one. They can be completely different. We can use just a spectrum. We can compress the spectral envelope in frequency domain instead of use Cepstrom. We can experiment using other sources, not just noise or pulse train. Okay, actually, we have done some experiments with using real speech as a source. And also, well, the question again. The phase, in this case, we have seen that the phase is just constructed from scratch. It's just invented. The phase is just created, and it has not been modeled, and also it's not recovered from the magnitude from other features. Like, for example, tachotron is a system that from the magnitude spectrum recovers the phase, or tries to recover the phase, and also there are some vocoders as the one that we will present in this interspeech that model the phase. Okay, so now I'm going to show some examples. We have system the Merlin plus world, and also Merlin plus straight. Straight is a vocoder, pretty standard, but it's closed source. You need to pay for that. And but it's pretty standard. There is receipts in Merlin as well. So let's listen to examples with feed-forward DNN bidirectional LSTM.
The steady drip is worse than a drenching rain. The steady drip is worse than a drenching rain. The steady drip is worse than a drenching rain. The steady drip is worse than a drenching rain.